Hello everyone. In this video, we're going to learn about p-series. A p-series is a series of the form sum from n equals a to infinity of 1 over n to the p, where a is some positive integer. Recall that we've actually seen an example of a p-series before, the harmonic series, which is the sum from n equals 1 to infinity of 1 over n. In this case, we have that p is equal to 1. In a previous lecture, we just stated that this series diverges, but we never really proved it. By the end of this lecture, we should be able to prove it for ourselves. So that leads us to the question, how do we determine if a p-series converges? The test that we're going to use to answer this question is called the integral test. The integral test says that if f of x is a positive decreasing continuous function on the interval 1 to infinity, so that f of n is equal to a sub n, then the series, sum from n equals 1 to infinity, of a sub n converges if and only if the integral from 1 to infinity of f of x also converges. In other words, if the integral from 1 to infinity of f of x converges, then the series converges, and if the integral diverges, then so does the series. We're not going to give a proof in general of this fact, but we'll talk about why it is true for a couple explicit examples. Before we go on, let's remember back to the lecture on improper integrals, where we learned how to compute the integral from 1 to infinity of 1 over x to the p dx. In particular, we found that it converges if p is greater than 1, and it diverges if p is less than or equal to 1. So now, as an example, let's compare the sum from n equals 1 to infinity of 1 over n squared to the integral from 1 to infinity of 1 over x squared dx. Now, from the fact that we just stated above, we know that the integral converges. So, by the integral test, the series converges as well. And let's see why this is true in this case. First, let's go ahead and graph the function. Now, the integral represents the area under this curve from 1 to infinity, which is represented by this pink region here. The series, on the other hand, can be represented by the area of a bunch of rectangles. For instance, the n plus 1 term is the area of the rectangle of width 1 and height a1, which is equal to f of 1. That's this blue rectangle here. Similarly, the n equals 2 term is the area of this rectangle, the n equals 3 term is the area of this rectangle, and so on. Now, how does the area of the pink region compare to the area inside the blue rectangles? Well, besides the first rectangle, all of the other rectangles lie inside the pink region. So, if we consider the nth partial sum of this series, the sum of the first n terms, we can rip off the first term, since the first rectangle is outside the pink region, to get 1 plus the sum from n equals 2 to n of 1 over n squared. Now, since the rectangles corresponding to the n equals 2 and above terms lie entirely inside the pink region, we have that this is less than 1 plus the area of the pink region, which is the integral from 1 to infinity of 1 over x squared dx. Finally, we can compute this integral just like we learned how to do before to get 1 plus 1, which is equal to 2. So, what we found is that all of the partial sums are bounded above by 2. More than that, though, the sequence s sub n is increasing, since all of the terms of the series are positive. Therefore, the sequence of partial sums is both increasing and bounded. And it's a fact that all bounded increasing sequences converge. Therefore, the series also converges, just like we wanted. A quick note, though, it is not true that the sum is equal to the integral. We didn't actually compute the sum using this process. However, it turns out that the series converges to pi squared over 6, which is actually pretty interesting. So, we just saw an example of why the integral test works for a convergent series. Let's see how it works for a divergent series. In particular, let's compare the series sum from n equals 1 to infinity of 1 over square root n to the integral from 1 to infinity of 1 over square root of x dx. Again, we'll graph the function, and now we'll shade in the region given by not the entire integral, but the integral from 1 to n. Then, just like before, we're going to draw rectangles representing the terms of the series, but we're going to do it a little bit differently. We're going to take all of the rectangles we drew before and shift them to the right 1 unit. So, the rectangle corresponding to n equals 1 will go right here, the n equals 2 rectangle will go right here, and so on. And we stop when we get to the last rectangle here, which is the n minus first rectangle. Now, just like we did in the last example, let's find a bound for the nth partial sum. In this case, we're going to find a lower bound. So first, we can say that the nth partial sum is bigger than the n minus first partial sum, since the nth partial sum includes one more term. But the n minus first partial sum is exactly the area of the blue rectangles above. Now, notice that the pink region lies entirely inside of the blue rectangles. So, the n minus first partial sum is bigger than the pink area, which is the integral from 1 to n of 1 over square root x. Taking limits of both sides as n goes to infinity, we get that the limit of the partial sums is bigger than the integral from 1 to infinity of 1 over square root of x dx, which we know goes off to infinity. Therefore, since the limit of the partial sums is bigger, it also must go off to infinity, and so our series diverges. Alright, that was a lot. It's not super important that you remember how these bounding arguments work. The point of all this is that we now have a very simple classification of which p-series converge and which p-series diverge. In particular, a p-series converges if p is greater than 1, since these are exactly the values of p for which the corresponding improper integral converges. And it diverges if p is less than or equal to 1, for exactly the same reason. And that's all there is to it. To make sure we're all on the same page, let's go ahead and do a couple examples. First, let's look at the sum from n equals 1 to infinity of 1 over the cubed root of n. To make this look a little bit more like a p-series, we can rewrite the series as the sum from n equals 1 to infinity of 1 over n to the 1/3 power. So we have a p-series with p is equal to 1/3, and since 1/3 is less than 1, the series diverges. Next, let's look at the sum from n equals 1 to infinity of n to the minus 15. Again, we can rewrite this to get the sum from n equals 1 to infinity of 1 over n to the 15th. And so, we have a p-series with p is equal to 15, and since 15 is bigger than 1, the series converges. Now, both of these series started at n equals 1. So does anything change if we start at a different value? For example, what if we had the sum from n equals 100 to infinity of n to the minus 15? It turns out that this series behaves exactly like the last example. It's just missing the first 99 terms. And so this series also converges, for the same reason the last series did. And finally, if we take the sum from n equals 100 to infinity of 1 over the 5th root of n, rewriting, we find that this is a p-series with p is equal to 1/5, and so this series also diverges.